Welcome to Module 4. In this module, we will learn about non-parametric tests. So this module covers chapter 7 from your textbook. In this module, we will discuss Mann-Whitney U-test, Wilcoxon rank sum test, Wilcoxon signed rank test, Kruskal-Wallis test. We will talk about John Keir Terpstra test, Friedman's ANOVA test, and also we will learn about ranking data, interpretation of results, and reporting results, and calculating an effect size for each of the above mentioned tests. A few notes from your previous module. In module 3, we discuss assumption testing in order to choose between parametric or non-parametric tests. So in module 3, we talked about assumption testing. If those assumptions are met, then we will go with parametric tests like t-tests, one-way ANOVA, z-test, Pearson correlation. If any of those assumptions was not met, then we have to choose non-parametric test, which includes Mann-Whitney U-test, Kruskal-Wallis test, Wilcoxon signed rank test, Friedman's ANOVA, and etc. And remember, the science or the math behind the non-parametric tests is that they rank data. So in order to kind of conduct non-parametric tests, we have to rank data first. But don't worry, SPSS will do that for us. So we don't have to rank data manually. So as I said, non-parametric tests are used when assumptions of parametric tests are not met. For example, the assumptions of parametric tests were linearity, normality, homogeneity of variance, independence, so on and so forth. And remember, when we talked about parametric tests and assumption testing, we mentioned some methods in order to correct data, like transforming data, bootstrapping, um, and th those kind of things, those kind of methods. But in some cases, we cannot just go ahead and correct data. So in some situations, we have to go with non-parametric test instead of correcting the problems we have in our data set. So in those cases, we have to use non-parametric test. And the good thing about non-parametric test is they assume no or fewer assumptions about the distribution of data. And in general, it is better to use robust test. But SPSS has some limitations regarding using some robust tests because those are really advanced statistical procedures. So in some cases, it is really difficult to evaluate whether our continuous variable, for example, let's say body weight, total cholesterol, blood pressure, these are all continuous variables and they can be our outcome of interest. And in some cases, it is difficult to evaluate whether they are following a normal distribution. So in those cases, a parametric or non-parametric test is appropriate. So, and remember, when we talk about evaluating the distribution of our data set, our data, we talked about several tests, like we talked about Kolmogorov-Smirnov test and Shapiro-Wilk test. which we saw in previous module. And also here is a quick note from previous module. So whenever the p-value for either of these tests was significant, we would assume that the data is not normally distributed. But if it was non-significant, we would assume that the data is normally distributed. So we would go with parametric test rather than using non-parametric test. So, and in some cases, it is obvious that the data is not normally distributed. Like whenever our outcome of interest is ordinal or a rank variable, because in those cases, we are 100% sure that an ordinal data, an ordinal variable, like let's say education level, which is an ordinal variable, or a rank variable, these are not normally distributed, which is obvious. So in those cases, we would go with non-parametric test. And in those cases, it is impossible to correct data. We cannot just kind of transform an ordinal variable or a rank variable to kind of correct the data and go and try parametric test. So in those cases, we would just stick with a non-parametric test. And also whenever we have some definite outliers in our data set. So because of outlier, we would assume that the data is not normally distributed because of outliers. We have so many outliers in the data set. So in those situations, we should go with non-parametric test instead of parametric test. So here are some advantages and disadvantages of non-parametric test. So as I mentioned, they make fewer or no assumptions regarding the normal distribution or other assumptions regarding parametric test. So it is one of the advantages of non-parametric test. We can use non-parametric tests with all scales. We can use nominal, ordinal, interval, and ratio for non-parametric test, but for parametric test, we cannot use ordinal or nominal variable. It's easier to compute, so if we have small sample size, we can kind of conduct the non-parametric analysis manually on a piece of paper if we have a small sample size. So that's an advantage for non-parametric test. It doesn't involve population parameters. So we don't have mean or standard deviation in non-parametric test. And in some cases, the results of non-parametric tests can be as exact as the results of parametric procedures. But we have also some disadvantages for non-parametric tests. First of all, it wastes information. Um, it's difficult to compute by hand for large samples. This is a disadvantage for non-parametric test. And also, unlike parametric test, we don't have any table for non-parametric test. So, for example, if you look at any statistics textbook, you would find some tables at the back of the textbook regarding uh, t-table or z-score tables, t-scores tables, but for non-parametric tests, we don't have such tables. For example, h-scores is not available for non-parametric test. H-score it's a statistic for non-parametric test. So there are two tests which are equivalent for the independent sample t-test. So we will talk about independent sample t-test in next modules, but just for your note here, let's say we have a continuous variable like blood pressure or total cholesterol. This is a continuous variable. It's a numeric and continuous variable. And we want to compare the mean of total cholesterol, for instance, between male and female. between someone who graduated from college and someone who doesn't graduate from college. So we have two groups, and we want to compare the mean of the continuous variable among between these two groups. In those cases, we will use independent sample t-test. But if our assumption, let's say total cholesterol is not normally distributed, for instance, and we don't want to transform the data, so we can go with a non-parametric test. Mann-Whitney U-test and Wilcoxon rank sum test is our option to use in this case. So these two tests, the Wilcoxon rank sum test and Mann-Whitney U-test, we use them either to test differences between two conditions in which different participants have been used, which is the Mann-Whitney U-test, and the means one group, this means one group versus another. This means a male versus female, not the same subjects before and after. So whenever we have pre and post data, let's say we measure total cholesterol before an intervention and after an intervention. So we are not comparing two groups of people here in this case. We are comparing the data, which is our total cholesterol, before and after on the same subjects. So this is where we will use Mann-Whitney U-test or Wilcoxon rank sum test. So, and here this is our Mr. Frank Wilcoxon, and thanks to him for developing these kind of tests and helping us to conduct our analysis. So as I said, the math and the procedure behind the scene of non-parametric test is ranking data. So we have to rank our data. So in this case, let's say I want to rank my total cholesterol. So the lowest score, I would give it a rank of 1, and the next highest score, I would give it a rank of 2. The next highest score, it will get a rank of 3, so on and so forth. So in this case, I ranked the data. And whenever we have a tied ranks, in that cases, I would compute the average of the potential ranks, and I will show you how to do that. And for an unequal group size, so let's say I have two groups, male and female, but I have 100 people as female and 50 people as male. So in that case, I have unequal group size. So in this case, the test statistic is Wilcoxon, which is the sum of ranks in the group that contains the least people. But for an equal group size, the test statistic, WS, is the value of the smaller summed rank. And then I would add up the ranks for the two groups and take the lowest of these sums to be our test statistic. And so in non-parametric test procedures, the analysis is performed on the ranks rather than the actual data. So we are not conducting the analysis using the actual data. We are ranking the data, and then we conduct analysis on the ranked data in cases of non-parametric test. So here's an example. It's like this is an example from your textbook. A neurologist investigated the depressant effects of certain recreational drugs. So we have 20 clubbers, 10 were given a tablet to take on a Saturday night, and other 10 were allowed to drink only alcohol, for example. And then we measured the levels of depression between these two groups. So in this case, I would go ahead and rank the data. I would assume that the levels of depression is not normally distributed. So our assumption testing is not met in this case. And then I have to go with non-parametric tests. And in order to do that, I have to first rank the data. So here is how rank the data. So let's say this is the I'm gonna rank the depression scores because depression scores is my continuous variable. It is my outcome of interest, and I have to rank that first. Then after ranking the data, I would compare the ranked data, not actual data, between groups. So our score is 3, 5, 6, 6, 7, 8, 9, 10, 17, 24. These are our actual data. The score is our actual data. So I want to rank it. So I would assign number 1, rank 1 to score 3, rank 2 to score 5 because I first I order the data, then I rank it from the lowest score to highest score. So here I have a tied score, 6 and 6. So in that case, I would assign a potential rank 3 and 4, and then I take the average of that potential rank, which gives me 3.5. It leaves me with 3.5. So that would be my actual rank. So then I would rank it 1, 2, 3.5, 3.5, and then 5, 6, 7, 8, 9, 10. Then the next highest score is 35, 35, 35. So in this case, then I would assign potential rank again, which is 16, 17, 18. Then I would take the average of the potential rank, which leaves me with 17, and 17 will be the actual rank for these three tied scores. So this is how I rank data for first group, which is my Wednesday data, and then I have Sunday data. Then I rank it again, just like above. Then I compare these two together, and that gives me the test statistic, and it gives me the p-value. And by looking at the p-value, I would say there is a significant difference between groups or not. So this is how it works. This is how non-parametric test works. So here is a YouTube video. I have put it here, and I also upload it to your Blackboard. Um, this is the author of the textbook explaining this example, and he is running different non-parametric tests one by one. I would like you to watch that very carefully, because I don't want to go into detail here about that. But so before, remember, in reality, in your own research, whenever you wanna conduct analysis, first you have to do some exploratory analysis in order to see if the assumptions are met or not. If the assumptions are met, then we should go with parametric test. If assumptions are not met, then we should go with non-parametric test. Or we can correct the data and go with parametric test. So first you have to do some exploratory analysis. And here we see the exploratory analysis. So we have QQ plots for depression scores for two groups on Sunday and Wednesday. And as I can see from this QQ plot, I can say the data, the depression score, it's not normally distributed because the dots, which are my observed value, um, are not are not located on the black line. So I would assume that the depression score, it's not normally distributed, and I don't want to go ahead and correct the data, so I would go with non-parametric test. And here is my test of normality, Kolmogorov-Smirnov and Shapiro-Wilk test, and the test of homogeneity of variance. So let's look at this. So Kolmogorov-Smirnov, the significance value for alcohol, for another drug is this is significant, but for the type for another type of drug, it's not significant. So for alcohol, it's not significant, but for ecstasy, is significant. So in these cases, I would assume that the data is not normally distributed. So I would go with non-parametric test. This is the same case with Shapiro-Wilk test as well. Let's look at the homogeneity of variance. So for the Sunday data, the Levin's test is not significant. For the Wednesday data, the Levin's test is not significant either. So I would assume that the test of the homogeneity of variance assumption is met in this case. So the variance of depression scores between two groups, alcohol and ecstasy, is similar to each other. The variance of two groups for Sunday and for Wednesday is not significantly statistically different from each other. So that assumption is met. The homogeneity of variance assumption is met, but since the test of normality is not met, then I would go with non-parametric test. So in order to go with parametric test, all of the assumptions we covered in module 3 have to be met. So here is the testing for normality. Uh, Alcohol is normal, but ecstasy is not normal for Sunday data. For Wednesday data, it's the other way around. So alcohol is not normal, but ecstasy is normal. So a non-parametric test should be used here because the assumption of normality is not met. Regarding the results of Levin's test, the assumption of homogeneity has been met since the Levin's test, here we look at the based on median. So based on median, Levin's test is not significant for Sunday and for Wednesday data. So the assumption of homogeneity of variance has been met. So how to do the non-parametric analysis? I will show you, but just for your information here, just a quick note about how to do it on SPSS. So we have to go to analyze and then choose non-parametric test and then independent or related depending on the data samples. So we have to choose independent samples or related samples. Then I would go ahead and drag and drop my variable into box. Then I can choose some options. Then I click OK. Then I would see my output in SPSS. So I'm going to show you how to do this. And this is the output I would see from the results. So this table, it's hypothesis test summary. It gives me significance, which is my p-value. One of them is not significant, another one is significant. So, and the test is independent sample Mann-Whitney U-test. And also it gives me some kind of graphs in order to compare the mean or median between two groups. Um, So the first column is for Sunday, which is not significant. The second row is for Wednesday, which is significant. And the decision column here, this is the output SPSS provides for us. So this is very useful. So in the decision column, here it says retain the null hypothesis, which means the null hypothesis is true. In other words, it is not significant. But the second column, the second row, On the decision column, it says reject the null hypothesis, which means the alternative hypothesis is true and the p-value is less than 0.05. So our hypothesis, our alternative hypothesis is met, which means there's a significant difference between two groups uh, here types of drug in my Wednesday data. And this is the Sunday and Wednesday data comparing together the graphs. And at the bottom, this is an output SPSS will provide. Here I have total N, which shows total sample size, total number of participants or observations in each group. I mean in total, not each group. And then it provides Mann-Whitney U-test, which is my U statistic, which is my test statistic. It also provides Wilcoxon, and then it provides standard error and the significance, which is here. It says two-sided test. And it gives me the p-value here for Mann-Whitney U-test. So based on this, I would assume that the data for Sunday is not significant. So there is no significant difference between alcohol and ecstasy for Sunday. But for Wednesday, the p-value is less than 0.05. It is significant. So I would say there is a significant difference between alcohol and ecstasy for Wednesday. Then I can calculate also effect size for Mann-Whitney U-test and Wilcoxon test. So in order to calculate effect size, you don't need to memorize these formulas. This is what SPSS will provide for us. But I can take the square root of sample size and then I divide the z-score by that value. It gives me R, and R is my effect size. So in this case, here in this table, it says standardized test statistic. This is my z-score. Then I would divide this by the square root of 20, and it gives me the effect size for Sunday and the effect size for Wednesday. So this is how I report my data for Mann-Whitney U-test. So I would say depression levels in ecstasy users inside the parentheses, I would provide the median. MDN is median. Did not differ significantly from alcohol users. And then again, inside the parentheses, I have to provide the median for alcohol group the day after the drugs were taken. Then I would provide the test results. So U stands for Mann-Whitney U-test, which is here. It says Mann-Whitney U-test in the table. Then I provide that one. Then I would provide the z-score, which is the standardized test statistics in the table. And then I have to report the p-value. And I can or I cannot. It depends on the paper. It depends on the researcher. I can provide the effect size, which is R, and we calculate it here by dividing the z-score um, by the square root of total sample size. So MDN is median, U is the Mann-Whitney U-test, Z is z-score, P is p-value, and R is effect size. This is how I would report the result. Or also we can report the Wilcoxon test instead of Mann-Whitney U-test. We have to follow the same you know, rule for reporting the result for Wilcoxon's test. But instead of having U test, I would say WS, which stands for Wilcoxon's test. And remember, median, the median is the value above and below which 50% of the data lie. And if the data is ranked in order, the median is the middle value. If we have odd numbers of, let's say, observations or participants, or odd numbers of people or data score, then the median will be the middle value. But if we if we have even number, let's say we have six score for depression, we have six data points for total cholesterol, then the median will be the average of the two middle values. And in symmetric distributions, as we saw in first module, the mean and median are the same. So that's why in parametric tests, most of the time we report mean, not median. But in skewed distributions, median is more appropriate than mean. That's why here in non-parametric test, we report median rather than mean. So another test is Wilcoxon signed rank test. So remember there are two types of Wilcoxon test. Let me go back and show you this. We have Wilcoxon signed rank test and Wilcoxon rank sum test. So Wilcoxon rank sum test is similar to Mann-Whitney U test, but in Wilcoxon rank sum test and in Mann-Whitney U test we have one continuous variable and we have two independent groups of people, and we want to compare the outcomes of interest between these two groups. But in Wilcoxon signed rank test, we have the same participants and we want to compare like the data score pre and post on the same subjects, on the same participants. That's the main difference between Wilcoxon rank sum test and Wilcoxon signed rank test. So here in Wilcoxon signed rank test, I compare two sets of score when the scores come from the same participants. As I said, we have pre and post. So imagine the experimenter, the researcher, was interested in the change in depression levels for each drug. So we have alcohol users and we have ecstasy users, and we have two time points, Sunday and Wednesday. And I just want to compare the Sunday data with Wednesday data for alcohol users. So I have the same subjects. I just want to compare the depression scores for the same subjects at two different time points. In that case, since the depression score is not normally distributed, I would go with non-parametric test, which in this case is Wilcoxon signed rank test, not Wilcoxon rank sum test. Just remember this main difference between these two tests. So again, I would go with non-parametric tests because the distribution of scores for both drugs were not normal on one of the days. So even though the depression score was normal for Sunday or Wednesday, for one of those days, the depression score for alcohol users was normally distributed. But since I have non-normally distributed data score for other day, I would go with non-parametric test. So the assumption of normality is not met in this case. So again, I would go ahead and rank the data. I would rank the data point, the data scores, the depression scores here. Then after ranking, then I would compare the results. So again, you don't have to do this manually. SPSS will do that for us, but this is behind the scene of what SPSS does for us when we are running non-parametric tests. Again, I would go ahead and open a dialog in SPSS. I would drag and drop my variables into test box. Then I can just click on a bunch of options and then I click OK and the results will pop up. But as I said, I apologize. The resolution for this picture is not good, but I will go ahead and show you on SPSS. And I would suggest watching the YouTube video. I have provided the link for it in a couple of previous slides. So here the output is again the SPSS will provide a hypothesis test summary. It provides the null hypothesis. It says the median of differences between baked depression inventory Sunday and baked depression inventory Wednesday equals 0. This is my null hypothesis. If the significance or the p-value is less than 0.05, I would assume that the null hypothesis is true, is met. Otherwise, I would reject the null hypothesis. So here the test is Wilcoxon signed rank test. The p-value is less than 0.05. So the decision for null hypothesis is I would reject the null hypothesis, meaning there is a significant difference between the median of depression scores between Sunday and Wednesday for alcohol users. And it provides a graph. Then I would see a table which provides the test summary for my Wilcoxon signed rank test. Again, it has total n, which is my total sample size. In this case, I have 10 participants for alcohol users. Test statistic is my Wilcoxon signed rank test. I have standard error. Standardized test statistics is my z-score, and then I have p-value, which is 0.012. It is less than 0.05, so it is significant. So there is a significant difference between depression scores uh, in on Sunday and Wednesday for alcohol users. So this is for the ecstasy group and this is for alcohol group. Again, this is a significant difference. For the effect size, it is the same way as for Mann-Whitney U test. So the formula is the same. I just go ahead and plug in the values in the formula and it gives me the effect size. And this is how I report. So here, Wilcoxon signed rank test is T. So T here it stands for Wilcoxon signed rank test. So how I should report the result in paper, in manuscript, I would say for XC users, depression levels were significantly higher on Wednesday. Inside the parentheses, I would provide the median. Then on Sunday, again, inside the parentheses, I would provide the median. The T stands for Wilcoxon signed rank test. I would report the p-value and the effect size. And here, I would go ahead and provide the Z score as well. Like instead of reporting the T, which is Wilcoxon signed rank test, I can report the Z score instead of T, which is stands for Wilcoxon signed rank test. Let's say I have a more than one group. I have a continuous variable, um, let's say total cholesterol or blood pressure or BMI. I have a continuous variable, which is my outcome of interest. But let's say I want to compare that continuous variable among more than two groups, not just two groups. Let's say I have three groups of people and I want to compare the um, total cholesterol among more than two groups. So for example, let's say I want to compare the total cholesterol levels among different race or ethnicity groups. So in that case, I have more than two groups. The the basic is the theory is similar to Mann-Whitney U test and Wilcoxon rank sum test, but since I have more than two groups, I would go with Kurzweil-Wallace test. So here is an example. Does eating uh, does eating soy affect your sperm count? So this is my research question. The variables, my outcome of interest is sperm count, which is a continuous variable. It's numeric and continuous variable, and this is my outcome of interest. My IV independent variable, my grouping variable, has more than two groups. I have no soy meals, four soy meals, seven soy meals. I want to compare sperm count, which is my outcome of interest across four groups. I have 80 males. This is my total sample size observations, 20 in each group. So in this case, let's assume the sperm count is not normally distributed, or the homogeneity of variance assumption is not met when I compare the variance among four groups. I have a significant difference in variances. So since the assumption testing is not met, I would go with non-parametric test. In this case, I would go with Kurzweil-Wallace test since I have more than two groups. If I had two groups, let's say I had outcome is sperm count and I had no soy meal and seven soy meal. In that case, I would go with the Mann-Whitney U test because I'm comparing outcome of interest between two groups. But here in this example, I have more than two groups. I would go with Kurzweil-Wallace test. So here again, I would go ahead and rank my data for sperm count for each group. For no soy, one soy meal, four soy meal, and seven soy meal. I would go ahead and rank the data. Then this is my test statistic. Kurzweil-Wallace test is represented by H. And this is the formula for H statistic. Again, you don't have to memorize or remember this formula. SPSS will do that for us. And if I go ahead and plug in the values, for example, I calculated manually. So I ranked the data, then I got total and average. Then I can just go ahead and plug in the value. It gives me the H statistic. So again, before running Kurzweil-Wallace test, I have to do some exploratory analysis in order to kind of test my assumptions. And here it says the data is not normally distributed, the sperm count is not normally distributed, and homogeneity of variance is not met either. So it's significant. The homogeneity of variance is significant. So none of the assumptions were met. I would go with Kurzweil-Wallace test. This is the SPSS. The author will show you how to do that in the YouTube video. And this is the results. Again, SPSS will provide the hypothesis test summary. which I can reject the null hypothesis or accept the null hypothesis. Then it will provide the summary, test summary. I have total sample size, which is 80 participants. Test statistics here is H, and the degree of freedom, it is 3. Degree of freedom in this case, it's number of group minus 1. So I have 4 groups. 4 groups minus 1 is 3. So degree of freedom is 3. And the p-value, which is significant. So I would say there is a significant difference in sperm count among 4 soy meals. Also, I can do some follow-up analysis after running the Kruskal-Wallis test. Here, I would assume that there is a significant difference in sperm count among 4 groups, right? But how can I say the difference is significant between group 1 and group 2 or group 2 and group 4? So in that case, I can do some follow-up analysis. So I would go ahead and do pairwise comparisons. For the pairwise comparisons, I would have 3 tests. So I would compare the 1 soy meal per week compared to no soy meal. Test 2 is 4 soy meal compared to no soy meal, and then 7 soy meal compared to no soy meal. And I can have more than this. Here is his keynote. If Kruskal-Wallis test is not significant, then there is no need to do follow-up analysis. If Kruskal-Wallis test is significant, which indicates a significant difference between groups among groups for outcome of interest, then I can go ahead and do follow-up analysis. Otherwise, there is no need to do follow-up analysis. So in order to do pairwise comparisons, there are different methods. One of them is stepped procedure, which is here. It's kind of comparing 2 groups at a time. Um, and this is how I would go ahead and do the pairwise comparisons in SPSS. Again, this is what the author will show you. This is the table for pairwise comparison between 2 groups. Again, it provides test statistic and p-value for us. And if the significance or p-value is less than 0.05, then I can say there is a significant difference for sperm count between, let's say, 7 soy meal per week and 1 soy meal per week. But uh, the p-value is not significant for 1 soy meal and no soy meal. Or it's not significant for 4 soy meal per week and no soy meal per week. But in general, overall, when I compare the 4 groups together, there is a significant difference. And this is how I would go ahead and report the output. So we have to only report the test statistic, and inside the parentheses the degree of freedom. As I said, since we have 4 groups, the degree of freedom will be 4 minus 1, and it means it's significant. And I would say sperm counts were significantly affected by eating soya meals. H is my Korskal-Wallis test. Inside the parentheses, my degree of freedom. And then I would report the test statistic and then p-value. And for the follow-up test, I would go ahead and write like this. Like I would say, there were no significant differences between sperm counts when people ate 7 soy meals per week compared to 4 meals per week. And inside the parentheses, I would go ahead and report the p-value and an effect size. Let's say if I have a I wanna kind of test for trends, I would go with another test, which is similar to Korskal-Wallace test. I don't want to go into detail about this test, because this is kind of an advanced statistical testing, but just for your information, and this is the output for that, this is the effect size, and how to report the result. The last one is Friedman's ANOVA test, which is a non-parametric test again, just like Mann-Whitney U test and Wilcoxon U test, Wilcoxon signed rank test, sorry. We use this Friedman's ANOVA test for testing differences between conditions when there are more than two conditions and the same participants have been used in all conditions. And again, if we violated any assumption of parametric test, we have to use this one. The Friedman's ANOVA test is represented by FR, and this is the formula. You don't have to remember the formula or memorize it. And remember again, we would go ahead and rank the data first, and then we plug in the values into this formula, and it gives us the test statistic, which is Friedman's ANOVA. So this is an example. This is my research question. Does the Andikin's diet work? So my outcome of variable is body weight in kilogram, which is a continuous and numeric variable. And then my independent variable or my grouping variable is baseline, 1 month, 2 months. So it is like time since beginning the diet. And I have 10 women. So again, my research question is, does the Andikin's diet work? Friedman's ANOVA is similar to Wilcoxon signed rank test, but we have kind of more than 2 time points here. So instead of having pre and post, we have baseline 1 month, 2 months, and we can have like 12 months, 24 months, and etc. So again, I would go ahead and rank the data, and I calculate the kind of total rank data, and then I plug in the numbers into the formula, and it gives me the um, Friedman's ANOVA test. So again, before running the analysis, I have to do some exploratory analysis first. So here I have non-significant values, p-values for Kolmogorov-Smirnov and Shapiro-Wilk test. So I would assume that the body weight is not normally distributed. And so I would go ahead and do the non-parametric test, which is in this case, Friedman's ANOVA test. So the Kolmogorov-Smirnov test is not significant for the initial weight at the start of the diet, but the more accurate Shapiro-Wilk test is significant. Since the Kolmogorov-Smirnov test is not significant, and also we have some non-significant values for Shapiro-Wilk test, I would go with non-parametric test. So this is the QQ plot. Again, it's not normally distributed. And then I would go ahead and drag and drop my variables into variable boxes, test boxes, and I can choose some options. Then I click OK. It gives me the output in SPSS. It also gives me the frequency for rank, and also it provides a table, which is my test statistic and the p-value. And the degree of freedom is 2 in this case. Why degree of freedom is 2? Again, I have 3 time points. I have at start or baseline 1 month and 2 months. So I have 3 groups. Degree of freedom is 3 minus 1 is 2. So degree of freedom is n minus 1. N means the number of groups. Here, there is no need to do comparison test or pairwise test since the Friedman's ANOVA test was not significant. So there is no need to do some follow-up analysis in this case. So for the reporting, the x to the power of 2 is my test statistic, or s squared is my test statistic. So I would say the weight of participants did not significantly change over the 2 months of the diet. X to the power of 2 inside the parentheses, my degree of freedom, and then p-value. This is how I would report the output of Friedman's ANOVA test. So to sum up, when data violate the assumptions of parametric test, we can sometimes find a non-parametric equivalent. It's usually based on analyzing the rank data. We have Mann-Whitney U-test and Wilcoxon rank sum test, which we compare two independent groups of score. For Wilcoxon signed rank test, we compare two dependent groups of score like pre and post. For Kruskal-Wallis test, we compare more than two independent groups of score. For Friedman's test, we compare more than two dependent groups of score. So for the assignment for this module, you would use the FACS 6350 module for data file, and you need to conduct two different non-parametric tests using the variables and then interpret results and explain findings. You would go ahead and use the module 3 write-up example again for this assignment. So I want to see some background, a section about methods, and the results section. And at the end, in the appendix, you have to kind of report and place the SPSS output at the end of your assignment document. So you need to choose two of these tests. It's totally up to you. And for this assignment, you don't have to do exploratory analysis again, just like what you did for module 3. So you would assume that the data, the variable is not normally distributed, so you would go with non-parametric test straight instead of doing some exploratory analysis. So for example, I chose total cholesterol 0, which is baseline, and gender. So I would conduct Mann-Whitney U-test since I have two groups, two independent group of score for total cholesterol. Total cholesterol is a continuous variable and gender is a categorical variable with two levels, male and female. So we have two independent samples. Total cholesterol is not normally distributed in either of the genders. I assume this. So we have to use Mann-Whitney U-test rather than independent sample t-test. So in SPSS, I would click on Analyze and then I find non-parametric and then I click on independent samples. This is what it gives me. So there's a table. I would drag and drop total cholesterol to test field and the grouping variable at the bottom, which is my gender, and then click OK, and it provides me this output. Then I would go ahead and uh, kind of report the results. I would say based on this table here, which is p-value is less than 0.05, I would say total cholesterol differed significantly between females inside the parentheses the median and males inside the parentheses the median for males. And then I would report the Mann-Whitney U-test, test statistic, the z-score, p-value, and I can calculate the effect size. So in order to get the descriptive statistics, which is the median, I would go ahead and I have to report the median. And this one, this table, this Mann-Whitney U-test, it also kind of, I would say, provides the median. It doesn't provide median, so I have to do some descriptive statistics in order to get the median. So in order to do that, in SPSS, I have to go to data option, split files, compare groups, then choose your grouping variable, click OK. Then I would go ahead and run descriptive statistics and it provides the median. But remember, after doing this, after getting the descriptive statistics for each group, you have to reset the split files before running the Mann-Whitney U-test. So I wanna show you how to do that in SPSS. So this is the module for data file. This is variable view. I have BMI 0, which is body mass index at baseline, BMI 1, 1 year, BMI 2 is 2 year. I have blood pressure at baseline, blood pressure at 1 year, blood pressure at 2 year. I have total cholesterol at baseline, total cholesterol at 1 year, and then gender, which is male and female. One is male and two is female. I have age, which is continuous variable. I have race, which is a categorical variable. I have marital status, which is a categorical variable, and this is a race, Mexican American, other Hispanic, so on and so forth. Income. Income is also categorical variable and other variables. So and this is my data view. So I wanna go ahead and do the non-parametric test, Mann-Whitney U test. So I would go to Analyze, Non-parametric test. I have independent samples. I would go to the fields. Total cholesterol is my test, outcome of interest, and gender is my grouping variable, and then click. So you can do settings, also go to the settings and customize and click on Mann-Whitney U-test. And also you can do median test, which is for follow-up testing. I don't want to do that here. This is test option, so I can kind of adjust the significance level. Instead of p-value less than 0.05, I can choose less than 0.01. I can also adjust the confidence interval. And this is for the missing value, so I don't want to do that. So just fields and then click run. And this is my non-parametric test. So this is table, which shows the significance, hypothesis test summary, and then p-value significance level. And it provides the table for Mann-Whitney U-test. So the total sample is 319. The Mann-Whitney U-test is my test statistic. And Wilcoxon rank sum test also here. Test statistic, standard error, z-score, and then p-value. And he also provides a table, a kind of a figure frequency. And I can see the difference between male and female in terms of uh, the total cholesterol here as well. So So, and then I report the man Whitney U test result. So I want to go ahead and do the descriptive statistics. So if I go to the analyze and then descriptives, and if I do the total cholesterol at baseline, and then I choose gender, let's see what happens. So here I don't see median. So it doesn't provide median here. So I have to close that. Let's try another way around. Let's do frequencies. But here is also another problem with frequency. Just let's try to see what happens. So total cholesterol, 0. And then I wanna put gender. I'm gonna unclick this. I don't wanna have a long frequency table. I click statistics and median and mean, minimum and maximum, standard deviation, skewness kurtosis. I don't want to do that. And then click OK. Let's see what happens. So here it gives me median, but it doesn't provide median between groups. Just provide the median for total cholesterol and the median for gender, which doesn't mean anything since gender is a categorical variable. So I cannot do some kind of ratio level of measurement um, statistic on that. So for that one, I would go to the data, split file, click on compare groups, drag and drop gender to this groups grouping box, and also you can just click on this and then click on this arrow and then click OK. And then I would go to the analyze descriptives, frequencies. I'm gonna remove gender and then total cholesterol. So here in this case, I would get median for total cholesterol for male and female. Then I can report this too. After after doing this, remember to go to the data and then split file and then reset and then click OK. Let's double check to see. Yes. Okay. So this is how you would work um, on this assignment um, for non-parametric test. And remember, again, you would you need to write the output just the same way as you did for module 3, and make sure to read my comments for your module 3 and kind of follow the comments and address all the comments and my feedback for your assignment 4.